is also in the filter. Okay? And an ultrafilter is a filter that's as big as you can make it. Okay? If you threw anything else into it, you'd get a contradiction because the complement of that thrown in thing would already be in the filter, and you get the empty set. The other thing I forgot to say is that these have to be non-empty sets. Okay, and so it turns out that any filter is embeddable in at least one ultrafilter. Okay, and the role of ultrafilters is that there's a theorem called Stone's representation for Boolean algebras. Okay, and Stone's representation theorem says, well, we know that a field of sets is a Boolean algebra, and the question is, are there effectively any other Boolean algebras? Is there any Boolean algebra that's not isomorphic to a field of sets? And the answer is no. And the proof of that assertion goes by saying, take an arbitrary Boolean algebra and define an ultrafilter on it, define ultrafilters on it, and the set of ultrafilters of the set of ultrafilters is the field of set, is the set omega, from which we can define subsets of ultrafilters that are isomorphic to the original Boolean algebra. And I'm going to use that theorem in my construction next. I'm not going to prove it, but I'll state the theorem. And it says, let's consider an arbitrary evidential structure. Then there exists a topological space and a mapping from the evidential structure to non-empty events in the topological space. Okay, non-empty open sets in the topological space. What is this mapping? Well, E stands for event. This mapping is precisely the downward mapping from evidential states to subsets of a state space. Okay. And I can moreover assume that the topological space into which I map is a compact space, that the images of evidential states are both open and closed, that the image of all of the evidential states is a base of the topology, that the only evidential state that maps into the whole state space is the root, that the more specific relation is represented by the subset relation, and the incompatibility relation is represented by the null intersection relation. Okay? So two evidential states are incompatible if there's no state of nature down here that's in the intersection of their images. Okay, and finally, every ultrafilter on the field of sets generated by the topology is definable in a sort of trivial way. There's some particular state of nature, and the ultrafilter is all of the sets that contain that state of nature. Okay. And a lot of this, for those of you who know Stone's representation theorem, is just dragged straight out of Stone. Okay. And these are properties of this mapping from evidential states to savage states, okay, that get used over and over again in the formal proofs of the theory, although I'm going to spare you the gruesome details today. Okay, now we've also been talking about evidential trees all along. And, I showed you back here a picture of an evidential structure that is not a tree. In fact, I've drawn some more on the board. Okay. But some of them are trees, and as discussion here has already shown, they're very important. Okay. So an experimentation tree, I want you to think of the experimentation tree as being the evidential structure of a scientist who keeps his lab books and doesn't let his RA forget the order of steps that were done. Okay, so an evidential tree basically is typically a subset of a bigger, an experimentation tree is a subset of a bigger evidential structure where the specificity relation on the tree is nicely related in ways that you don't have, if you can't focus on the text here, it doesn't matter. It's nicely related to the underlying specificity on the structure from which it's derived. Okay, and again, this is mostly something that probably could have been deleted from the talk. And the real point of it is simply I can put down axioms that define a tree as a graph, okay, and that have one or two extra nice properties that basically are inherited from the evidential structure in which the tree lives. Yes?
So, if the world is represented as an answer to 10,000 binary questions, and of course our knowledge is a point on it that's given by the answer to some of those questions.
Yes.
Then this is a tree structure. Not only it's a tree structure, it's a very symmetric tree structure in the sense that there's the same a regular tree structure, the same number of branchings at each.
Well, wait, I don't think it is a tree structure.
Why not?
I suppose I know that there was a heads on the first toss. There was a heads on one toss. I see.
No, I know the questions are anonymous.
You know the order of tosses.
I don't necessarily I mean, it's not or the order of tosses. Well, I know what the questions are. I don't know whether the answer yes refers to a finding of the.
Suppose you're a chemist with a sample, and you know the weight of the sample, and you know what element the sample is made of.
Mm-hmm.
Okay. Well, there are two less specific evidential states above that. You know the weight but not the composition, and you know the composition but not the weight. Okay. And those are immediately less specific than your actual evidential state. But to be a tree, every evidential state has to have a unique, one step less specific predecessor.
Mm-hmm.
Okay? So here's a chemical example. We've got a sample, and it's one of three. These elements are called metalloids: germanium, arsenic, and antimony. Okay, and they of course have compounds. One type of a compound with them is a pentoxide. Okay, it attaches itself to 5 oxygen atoms, and it turns out that one of these, germanium, does not have a pentoxide compound, but the others do. Okay, and so I'm going to give you these labels. The chemical name of the compound is just going to denote some compound of the element. Okay? A question mark before pentoxide means we know it's a pentoxide molecule, but we don't know which metalloid the oxygen is combined with. Okay? The complement to that event is double question mark, meaning we don't know which metalloid is in it, and except for knowing it's not a pentoxide compound, we don't know what else the metalloid is combined with. Okay? And then, of course, there are the maximally specific. It's either germanium, well, it's a pentoxide compound, or the germanium compound, I guess. So here are the E structures, evidential structures, that correspond to that. Okay, we've got the root. Okay, and we know next level. We know either that it's an arsenic compound, or that it's a pentoxide compound, but not both, or that it's an antinomy compound, or that it's either a germanium or a non-pentoxide compound of something else. Okay, that's the intermediate level. And then the most specific level that the chemist could get to, given the limited equipment he has in his laboratory, is he knows either it's a non-pentoxide compound of arsenic, or it's arsenic pentoxide, or it's antinomy pentoxide, or it's antinomy something else, or it's a germanium compound. Okay. Now, there are two experimentation trees that are worth looking in this. Suppose you're only interested in which metalloid is in the compound. Okay. And you want to do a quick and dirty test to figure that out. You're not interested in whether or not it's a pentoxide compound. So then you can do just one round of experimentation, okay, and you find out it's either an arsenic compound, or it's a antinomy compound, or it's a germanium compound, and you're done. You don't know everything, but you know the answer to the question that you care about. There's another two-step experimentation tree. Okay, and you might ask, first of all, is it a pentoxide compound, or is it something else? And if it's pentoxide, then at the second level, you ask, is it arsenic or antimony? Okay, and if it's not a pentoxide, you ask, is it germanium, or is it some other compound of arsenic or antimony that's not a pentoxide? Okay, so this gives you, if you're only interested in the metalloid in your compound, this sometimes gives you more specific information than you really care about. Okay, the point is, these are trees. Okay? They fit the whole definition of my definition of an experimentation tree. Okay, and you know, based on the cost of doing various tests and so forth, it might be that either of these would be the better one for some chemist or other to use, what equipment he's got in his laboratory. So here's another thing, and this is also a tree. Okay, just do one experiment and find out it's either a pentoxide compound, or it's a germanium compound, or it's some or it's some compound of antimony. Okay, and this is not an experimentation tree, and I want you to understand why. It fails to be an experimentation tree in two respects. Okay, this is the slide I skipped over and told you not to worry about the details, but now I want to give you the intuition. Okay, So the first thing is there's a compound, antimony pentoxide, that is more specific than either of these two outcomes. Okay, and so we couldn't do another round of experimentation and be guaranteed to have a tree. Okay. In fact, if this is a truth, then there's a question, will we observe this or will we observe this when we do our experiment? Okay. And our notion of an experiment ought to be, we do the experiment and it partitions the possible truths into some corresponding to this experimental outcome and others correspond to that with nothing in common. Okay. The other problem is that what if the truth is that it's an arsenic compound and then there's no outcome of this tree that's consistent with this? Okay. So part of the notion of an experimentation tree is whatever is true, there ought to be some experimental outcome that at least gives you the partial truth of that entire truth. Okay. So the point of this slide is to say that being an experimentation tree, the first thing is to say evidential structures typically have experimentation trees as substructures. And moreover, not every graphical tree is an experimentation tree. There are further conditions to be put on it to flesh out our intuitive understanding of what we mean by an experiment or what we mean by an experimental plan, sequence of experiments. Okay. Now it turns out that an experimentation tree, if you just forget about the structure in which it lives, it's an experimentation tree in itself. And that's very convenient, of course, because we can just talk about an experimentation tree without having to specify what structure it lives in. Okay. Now, how is an experimentation tree related to its canonical field? Well, there's a filtration. Okay. Histories are now known. Okay, and histories in stochastic process theory produce filtration. Okay, and when we analyze these filtrations, we get proposition 5 here, which says if we take this downward evidential map from the E states in an experimentation tree to the savage states in the mental construct that represents it, if you will, what we get is a sequence of finite Boolean fields, okay, and their union is the, since they're finite, it's trivial to complete them to a countably additive, finitely additive and countably additive the same. Okay, if we take their union, what we get is the Boolean field, but not the countably additive sigma field on the topology in our representation theory. Okay. Now I've already shown you how coin tossing with equivalence of countably order statistics loses track of history and you don't get an experimentation tree. Finally, I'm going to get to actions. Okay? And I'm just going to say we're going to have primitive choice alternatives, which I'll call any acts, there's a set of them, and for mathematical convenience, it's finite, and for non-triviality, there are at least two alternatives. Okay? And if I've got a subset of an evidential structure, and the mapping of that subset to actions, then I'm going to call this mapping a plan. Okay. Plan says for any evidential state I happen to be in, what I would do based on that evidence. Okay? And I'll call it a tree plan if its domain is an experimentation tree, not just an arbitrary subset of an evidential structure.
What was last line, please?
It's just defining what I mean by when I say a tree plan. This line?
Okay, no, go ahead.
Okay. Now, a conditional preference relation is a family of preference relations, preorders, that are indexed by the evidential state. So I've got one preference relation when I've seen heads on the first toss, and I have another preference relation. This is on betting heads or tails on the next toss. I've got another preference relation when I've observed tails on 3 succeeding tosses, and so forth. Okay. And I'm going to say that a conditional preference relation is immediate strict dominance consistent if, remember, y of z is the set of immediately more specific evidential states. Okay. And I'm going to say that if you'd prefer B to A, no matter what additional bit of evidence you got beyond your current evidential state, you ought to already know that you prefer B to A, because that additional bit isn't going to be decisive for you.
Could you go a bit slow on actually both these things, 33 and 34?
Okay. 33 simply says we've got a family indexed by evidential states of weak preference relations, okay, and ordinal preference relations. And so having different evidence, because you're, as a Bayesian, you're conditioning on your evidence, having different evidence will typically give you a different ordinal preference relation over X.
So this is just a binary relation over X. Now do you want me to understand a bit more than that? Than simply a binary relation?
No, that's all it is.
Okay. But now you are saying something else because you're putting meaning in 34. Right?
Okay. Now I'm telling you that this is a kind of a candidate for a rationality condition.
Exactly.
Okay. It says if my conditional preferences are making rational use of evidence.
So what does that mean? So could you please?
I'm not necessarily advocating this.
Yeah, fine, that's fine.
Okay,
But let's understand this.
Okay.
So y of z is the set of immediately less or formative for lesser. Can you remind us? More informative. Immediately more informative.
Let me flesh out in detail. Suppose I am you know, 999 out of 1,000 certain that a particular coin is biased towards heads. Okay, and you know, the experimenter tosses the coin puts it under a cup. I've still got coffee in it, so I better not demonstrate this.
That's exactly that.
Okay? And says,
Do I want this information?
do you want that on heads or tails? Okay.
With one pen.
And you say, and you know, I get my cell phone and I take a photo of it to record that, and then I toss the coin okay? And if it comes up heads, you say, how do you want to bet? And you say heads. And if it comes up tails, and I ask you, how do you want to bet? Well, remember, you're 99.9% sure it's biased towards heads. Then you still say heads, okay? Now suppose, before I had tossed the coin and let you see the outcome, I had asked you to make a bet. It would be irrational of you to have bet on tails, because you should have foreseen that once I showed you a toss, regardless of the outcome, you were going to bet on heads. Why didn't you bet on heads to begin with? Okay.
Except for the fact that what makes
so that's,
me uncomfortable here is that, if we are already getting into bets which give me value and stuff, here there is evidence, because we're still.
well, I'm saying,
I'm
if you're not going to use an additional piece of evidence,
But in choosing an act, or again, already I'm using the word choosing. I mean, this is just a binary relation. And all of a sudden-
It's preference.
Yeah, now it's, yeah, okay, but it's okay.
But if your choice does not depend, well, to express this as choice, if your choice does not depend on a bit of evidence, then the presence of that bit of evidence should not affect the choice.
that's right.
Sure.
Another way to, if you know you're going to go for a walk, regardless of the weather outside, you don't need to look out the window.
I understand that. See, the point is the
That's-
moment
yeah.
you tell me, like an act, going out for a walk, etc., I can put meaning to them.
Mhm.
My point is here, act has been defined as just, so a set of act has been defined, and there is a mapping which maps from a domain to act,
Right.
right? I don't know what those acts are. Now, if you say walking, I understand a lot. In fact, I don't even understand what I understand. But
Yeah.
here,
Okay.
You're
Normally, if I were a better seminar giver, I'd pursue this, but I'm at the verge of overshooting my time limit, and I have to cut it off. Okay? But you understand this formal, whether or not you like it, you understand, right? Okay? And then I define conditional subjective expected utility maximization in a way that you understand what I mean. That there's an underlying measure on this savage state space down here. There are state-dependent utility functions for the various acts, and this conditional preference relation is spelled out in terms of the integral for one act being higher than the integral for the other act. Okay, now I'm going to say that a conditional preference relation rationalizes a plan if the action chosen at an evidential state by the plan is revealed preferred to any other action. And I told you I was going to do revealed preference theory, and this is it. Okay, and I'm going to say plan is rationalizable if there's some expected utility representable conditional preference that rationalizes it. Okay, and here I formalize this, but since I'm running short of time, yes?
We're talking real preference, and there's been a lot in here. What is the data I need to write this real preference
Okay,
relation?
the evidential state corresponds to a budget set.
Yes.
It's the evidential states. So in demand theory, budget sets are the various situations in which the agent might find himself. Here, evidential states.
And I'm trying to get, for each evidential state,
The person.
I'm getting the binary relation.
Right.
So it's a collection of binary relations for different evidential states. That might be different.
Okay. So what I want to prove for tree plans, this consistency condition that we put up and discussed for a moment actually turns out to be necessary and sufficient for Bayesian rationality. But for general evidential structures, it's neither necessary nor sufficient. And let me finish up by giving you two quick examples. Here what I've done is I've taken an evidential structure, okay, and there are 9 nodes in the tree, the root, 3 intermediate nodes, and 5 maximally specific nodes. Okay? And these arrows just show what the plan says. So there are 2 possible actions, A and B. And, okay. Now what's going on here, for any intermediate evidential state, the agent prefers B, but at the root the agent prefers A. That's violating my consistency condition. Okay. The problem is that the maximally specific evidential states are being triply counted. Each of them is the child of 3 distinct intermediate states. So let me tell you, so it's clear what the Savage state space for this is going to be. Okay, it's just the power set of the maximally specific states. Okay, and so let's call the Z's to be the states of nature. Okay, and an action is going to have utility 1 at a state of nature if it's chosen at that state of nature, and 0 if it's not the chosen action. Okay, and now I'm going to put uniform measure. Probability of each Z is 1/5. Okay, and therefore, when there are 3 children of a node, the expected utility chosen action is determined by majority vote, given that they're 3 equal probabilities. Okay, so X1 has children Z1 and Z2, Z4 and Z2, Z4 and Z5, both of which have B chosen, and Z2, which has, no, Z1, which has A chosen, so B wins 2-1. Okay, and you can do the other at these other 2 intermediate nodes, and that explains why B is the expected utility maximizing choice at every intermediate node, but at the root, A wins 3-5. Okay, so this uniform probability measure and 0-1 utility gives me an expected utility rationalization of this plan, even though the plan violates the sure thing like consistency condition. Okay, and let me go in the opposite direction. Here's our favorite example of the coin tosses where you forget the order. Okay, and I'm going to say that A is chosen here and here, B is chosen here and here, C is chosen here and here. Okay, again, the Savage state space is the power set of the Z's. Okay, and so I'm going to assume that this plan is rationalizable, and I'm going to derive a contradiction. Okay. I'm going to look at the root, and so my plan says A is the most preferred act at the root. But now I want to ask, hypothetically, if A weren't available, would I choose B or would I choose C? Okay, and I'm going to use the sure thing principle. Okay, the salvage event of the root is the set of these things. Okay, and C is preferred here, and C is preferred in the event that it's one of these two other states. So by the sure thing principle, C should be preferred to B up here. But wait, B is preferred to C here, and B is preferred to C in the event that it's one of the other two states. So by the sure thing principle, B should be preferred to C here. I've gotten the contradiction. Okay, so I can't rationalize this plan by expected utility. Okay, but notice that in order to violate my consistency condition, you've got to have unanimity at all the children of the node. Okay, and in this example, there's no node that has unanimous children. Here it's B and C, here it's C and A, here it's A and B. Okay? So the consistency condition holds vacuously, and therefore the consistency condition is not sufficient for expected utility rationalizability. Okay, thank you very much.
Any questions? Thank you. Someone